The early morning fog clung to the edges of the airfield like a curtain hiding secrets. German engineers, still rubbing sleep from their eyes, walked cautiously among the twisted metal and scattered debris of the latest air battle. The distant rumble of retreating engines and the faint echo of anti-aircraft fire hung in the air, a reminder that the sky was still a deadly chessboard. But what they were about to see would leave them speechless. Not a battlefield victory, but a puzzle. A machine that defied expectation. There it lay, a P-47 Thunderbolt, its massive radial engine exposed as if daring them to understand its power. The engine's sheer size alone was intimidating, a coiled beast of polished steel, intricate piping, and roaring cylinders that seemed alive even in its silence. One of the engineers, a veteran of countless German designs, stepped closer, tracing the contours with gloved hands. He had built some of the finest engines the Luftwaffe had ever known, BMW 801s, Daimler-Benz DB 605s, but nothing prepared him for this. 2,000 horsepower, compact, brutal, relentless. Whispers moved through the group. "Impossible," muttered one. "How could they make this? And so fast?" Another simply shook his head, staring at the complex network of superchargers and cooling fins, the meticulous arrangement of valves that seemed both elegant and terrifyingly efficient. It wasn't just power. It was reliability, endurance, a confidence in design that no German machine they had seen could match. Outside the engine hangar, the world carried on as if nothing had changed. Allied fighters roared overhead, and somewhere beyond the horizon, bombers carried their deadly payloads. Yet in that small, shadowed airfield, a quiet reckoning was taking place. Here was a secret that would challenge German engineering dogma, a truth that whispered. Even the brightest minds could be humbled. The engineers flipped through hastily captured manuals, their eyes darting across diagrams filled with dimensions, tolerances, and specifications. Every calculation seemed to underline the same impossible fact. The Americans had achieved what Germany could not. Every rivet, every cylinder, every crankshaft spoke of a philosophy that the German designers struggled to comprehend. It was not merely about raw power. It was about an industrial vision, a way of thinking about machines as more than mechanisms, as tools to endure, to dominate the skies relentlessly. And yet, even as awe and disbelief battled within them, the engineers understood that this discovery was not just a technical curiosity. It was a warning. The Thunderbolt, in the hands of skilled pilots, was a weapon that combined speed, firepower, and invincibility in a way that would shape the skies of Europe for months to come. A single engine could shift the balance of air power, turning desperate skirmishes into decisive clashes. Outside the hangar, the sun began to pierce the fog, illuminating the massive radial cylinders like golden towers. The engineers gathered closer, some taking notes, others sketching diagrams, and a few simply staring in silence. The question loomed over them, heavy and insistent. How had the Americans done it? And could we ever hope to replicate it? This was more than an engine. It was a revelation, a challenge, a subtle but undeniable turning point. The captured P-47 didn't just speak of power, it spoke of ingenuity, ambition, and the relentless pace of technological warfare. And for the men standing there in gray uniforms, it planted a seed of doubt that would grow over the coming months. A realization that the war in the sky was not only fought with bullets and bombs, but also with ideas, and that some ideas, once set in motion, could not be matched. In the silent tension of that misty morning, one thing was clear. The world had changed. And the race to understand, to replicate, to surpass this marvel had just begun. The Americans had crafted a machine that defied expectation. And Germany was left staring, frustrated and fascinated, at the heartbeat of an engine that could turn the tide of war. Why did the Americans succeed where even the most brilliant German minds faltered? What secret lay in the mechanics of the Thunderbolt's heart? These questions would haunt every engineer, every designer, and every commander who dared to face the skies after that fateful day. And as the sun climbed higher, revealing the glinting steel of the P-47's massive frame, the answer seemed simultaneously simple and impossible. America had built not just an engine, but a legend. By 1943, the skies over Europe had become a lethal theater of constant innovation and desperate adaptation. From the frozen plains of Russia to the bombed-out cities of France, air battles raged relentlessly. On one side, the Luftwaffe wielded its formidable arsenal, sleek Messerschmitt Bf-109s slicing through clouds like silver daggers, Focke-Wulf FW-190s that seemed to dance with deadly precision, engines humming with the perfection of German engineering. Every sortie was a testament to training, discipline, and decades of meticulous design philosophy. Yet across the Atlantic, American industry moved at a pace that defied imagination. Factories in Detroit, Philadelphia, and Hartford churned out aircraft and engines with a relentless rhythm, fueled by raw horsepower and unyielding manpower. The P-47 Thunderbolt, the so-called Jug, emerged from this machine-driven crucible, a behemoth of a fighter powered by the mighty Pratt Whitney R-2800 double wasp, a radial engine capable of delivering 2,000 horsepower. It was heavy, it was fast, and it was seemingly indestructible. To the Americans, it was simply the right tool for the job: to escort bombers deep into enemy territory, to dominate the sky, to survive. Air combat, however, was never solely about numbers or brute strength. In the early days of American engagement, pilots quickly learned that tactics honed against Japan's nimble Zeros were inadequate against Germany's disciplined squadrons. The Focke-Wulf FW-190s, with their superior roll rates and acceleration, punished any pilot who underestimated them. The skies were an arena where a single miscalculation could end in fire and metal, where every maneuver had life-and-death consequences. It was in this crucible that innovation began to emerge. The Thunderbolt, initially criticized for its weight and lack of agility compared to the nimble Messerschmitt, soon revealed its hidden strength: sheer durability and engine resilience. Unlike the delicate high-strung German power plants, the R-2800 could withstand extreme conditions: sub-zero altitudes, extended combat, even minor battle damage, without faltering. Its reliability allowed pilots to push the P-47 to limits that other aircraft simply could not survive. The German engineers, confident in their technical superiority, initially dismissed reports from the front. How can a plane so heavy match the agility of a Bf-109, they mused. Yet the stories kept coming. Pilots surviving near impossible dives, escorts shielding bombers deep into enemy territory, missions where every other aircraft would have fallen. Behind each account lay the same engine, working flawlessly, humming like a mechanical heartbeat that refused to be silenced. Commanders on both sides watched these developments closely. General Dwight D. Eisenhower's strategies relied increasingly on air superiority. Each P-47 that could escort bombers over Berlin reduced losses and strengthened the Allied advance. Meanwhile, Luftwaffe officers like General Adolf Galland and Ernst Udet pored over captured reports, trying to discern the secret behind these American feats. Was it training? Luck? Or had the Americans discovered something the Germans could not replicate? On the technical side, engineers such as Kurt Tank, designer of the FW-190, began comparing notes with their teams, examining photographs and schematic diagrams, trying to understand why the P-47's engine was outperforming their finest designs. Every observation only deepened the mystery. How had the Americans achieved 2,000 horsepower in a radial engine that weighed so little and yet remained so reliable? The industrial and material constraints of wartime Germany made replication seem nearly impossible. Aluminum, high-octane fuel, precise machining, resources that Germany struggled to maintain, were all abundant in the United States. Meanwhile, American pilots experienced the growing confidence that came from knowing they could rely on their machines. Tales circulated of Thunderbolts shrugging off enemy fire, returning home from missions that would have grounded other aircraft, and turning near-certain death into survival. The Jug became more than a plane. It became a symbol of technological ingenuity, a steel guardian of the skies. And as the war pressed on, the contrast between the two approaches grew ever starker. German engineering remained brilliant, precise, and beautifully complex, but vulnerable to the pressures of attrition, resource scarcity, and the unforgiving realities of mass production. American engineering, by contrast, embraced scale, reliability, and sheer adaptability, producing machines that could be flown, repaired, and maintained under conditions that would have crippled their counterparts. In that tension between perfection and pragmatism, the stage was set for the moment the German engineers would encounter the captured P-47. What they saw was not just an engine, it was a manifesto of industrial philosophy, a challenge to their assumptions, and a harbinger of the changes the skies of Europe were about to endure. The technical battle, it became clear, was inseparable from the battlefield itself. The engine beneath the cowling of the Thunderbolt was more than metal and pistons. It was a weapon that reshaped strategy, morale, and the very course of the air war. By late 1943, the Luftwaffe faced a troubling reality. Their once dominant air force was being tested in ways that engineers and pilots had not anticipated. Every mission over the Western Front revealed a painful truth. Messerschmitts and Focke-Wulfs, though marvels of precision engineering, were increasingly unable to assert dominance against the rising tide of American aircraft. Pilots returned from sorties, eyes haunted, tales of Thunderbolts shrugging off hits, engines still roaring, and bomber formations escorted deep into German territory. Inside the design bureaus of Germany, frustration simmered. Kurt Tank and his colleagues pored over flight reports, schematics, and captured parts from American aircraft, each revealing a sobering pattern. German engines, despite their elegance and ingenuity, could not match the sheer endurance and output of the P-47's Pratt Whitney R-2800. Every analysis exposed the same weaknesses: engines that overheated under prolonged high-power use, components that wore out faster than could be replaced, and tolerances so precise that field repairs often failed. Their most brilliant minds confronted a sobering paradox. Technology that was perfect on paper was failing in practice. Losses mounted, and the toll was both material and psychological. Pilots flying Bf-109s found themselves outmatched in speed and resilience. Dogfights that once favored German craft now ended in retreat. Reports described engagements where Thunderbolts absorbed damage that would have grounded any German fighter, returning pilots safely to base while their adversaries watched helplessly. The engineers' pride, built on decades of meticulous design, faced the harsh glare of reality. Their creations, masterpieces in isolation, could not sustain the rigors of prolonged war. The stress in German factories mirrored that in the air. Resources were scarce, raw materials diverted to other fronts, and skilled machinists in short supply. Every design iteration took months to implement, yet even the most advanced engines could not replicate the R-2800's combination of power, reliability, and simplicity. The engineers' meticulous attention to detail, once their greatest strength, became a limitation, a perfection that could not adapt to the chaos of total war. Historical accounts highlight specific missions that underscored the crisis. During the Allied bombing raids over Schweinfurt and Regensburg, German fighters engaged enormous formations of P-47's. Pilots reported engines overheating after extended climbs, hydraulic failures under stress, and metal fatigue in components that had been considered indestructible. Each engagement confirmed the same uncomfortable lesson. Tactical skill alone could not compensate for the limitations of German engineering under wartime pressures. Amid these defeats, the psychological burden weighed heavily. Engineers felt a creeping doubt that perhaps the enemy had discovered an advantage they could not outthink or outdesign. Memoirs from Luftwaffe personnel reveal moments of quiet desperation. Long nights spent examining engine diagrams, arguing over tolerances and materials, and yet never arriving at a solution that could match the American powerhouse. The very concept of replication seemed impossible. Each test revealed not just a technological gap, but a fundamental difference in industrial philosophy. One captured P-47, its engine intact, became the centerpiece of this growing anxiety. Every inspection, every measurement, every calculation served as a reminder that the Germans were confronting more than just a machine. They were facing an industrial ideology that prioritized resilience and mass production as aggressively as they pursued technical brilliance. The P-47's engine, simple yet extraordinarily effective, highlighted the limits of German methodology. Engineers realized that no matter how brilliant the design, a system that could not be reliably produced at scale would always lag behind. This moment marked a turning point. The German technical community recognized that continuing along the same path, focusing on perfection at the expense of practicality, was a dead end. To close the gap, they would need to rethink their approach entirely. But the challenges were formidable. Material shortages, time pressures, and the relentless march of Allied production created a sense of inevitability. For the first time, the Germans faced the stark truth. The war in the air was being decided not just by skill in combat, but by the industrial ingenuity of the Americans. And so, in workshops and hangars across Germany, engineers began to ask the questions that would define the rest of the conflict. Could the R-2800 be studied, analyzed, and understood? Could its secrets be replicated without the same resources and industrial capacity that America enjoyed? Each unanswered question deepened the sense of crisis, and every failed attempt to match the Thunderbolt's performance reinforced a sobering realization. The Germans were encountering a technological wall that could not be scaled with conventional methods. The stage was now set for the next phase of discovery, a desperate search for innovation, for inspiration, and perhaps for a breakthrough that might allow German engineers to regain parity in the skies. But the lessons of the captured P-47 loomed large. The gap between brilliance and practicality was not just an academic problem. It was a matter of life, death, and the outcome of the war itself. The captured P-47 sat under harsh halogen lights in a crowded German hangar, every shadow exaggerating its formidable silhouette. Engineers circled it, like scholars examining a rare manuscript, each step measured, every glance searching for insight. The R-2800 double wasp engine gleamed with a mechanical elegance that defied expectation. 2,000 horsepower, a compact radial layout, and resilience that mocked their own carefully engineered designs. It was more than a technical marvel. It was a revelation. Kurt Tank and a small team of top engineers embarked on what became a fevered investigation. They dismantled the engine meticulously, documenting every component, tracing every pipe, and mapping every cylinder's stroke. Precision instruments measured tolerances. Thermodynamic calculations attempted to model airflow, compression, and heat dissipation. Yet for every insight gained, two more mysteries emerged. The Americans had not only created raw power, they had done so with a simplicity that German methodology struggled to reconcile. Each innovation, from the supercharger design to the reinforced crankcase, was as much about practical resilience as it was about mechanical ingenuity. Meetings with Luftwaffe command were tense. "We must understand this engine," Tank emphasized, his voice echoing in the cavernous hangar. "If we can replicate even part of its power, we may regain parity." Some officers, skeptical, muttered about time wasted, arguing that the front lines demanded fighters now, not analysis. Others feared that the very act of study admitted defeat. The Americans had out-engineered them, and every hour spent examining the Thunderbolt was an hour their own production lines fell further behind. Despite the tension, the engineers pressed forward. They devised experimental test rigs, running small-scale components under extreme loads to simulate the R-2800's performance. They noted the engine's tolerance for high-octane fuel variations, its ability to maintain output under prolonged combat conditions, and its cooling efficiency, an area where German designs often faltered. Each test revealed a subtle truth. The Americans had engineered not just for performance, but for survivability, mass production, and field reliability. The first attempts to emulate the R-2800 yielded mixed results. Prototype components melted under stress, tolerances failed, and materials warped. Yet within the hangars, a cautious excitement began to replace frustration. Engineers began to see patterns, not just in the engine's design, but in the philosophy behind it. Simplicity, resilience, and scalability were not limitations. They were strengths. The breakthrough was not a single component or diagram. It was the realization that industrial vision mattered as much as engineering precision. Field tests, conducted in secret, confirmed their suspicions. Engines built to mimic the Thunderbolt could produce impressive horsepower, but reliability remained elusive. Components failed, cooling systems buckled, and the fine balance between power and endurance proved delicate. Reports from pilots flying these prototypes were sobering. Even minor deviations from the American design led to catastrophic failure. The Germans understood that replication would be near impossible without access to the same resources, tooling, and production methods. Yet, even in failure, there was progress. Engineers began adapting lessons, rather than attempting perfect copies. Cooling systems were redesigned, material use optimized, and assembly methods simplified. While they could not produce a true R-2800, they began to integrate its principles into new designs, incremental improvements that might bridge the growing technological gap. The first combat encounter using modified engines was telling. Pilots reported slightly improved performance, more reliable operation under stress, and better endurance at altitude. It was not the Thunderbolt, but it was progress. A demonstration that understanding the philosophy behind the machine was sometimes as valuable as the machine itself. For the engineers, this moment marked a subtle shift in thinking. The captured P-47 had served not just as a technical object to be dissected, but as a catalyst for strategic reflection. German command realized that technological superiority could no longer rely solely on perfection or ingenuity in isolation. It required practical adaptability and industrial foresight. The Thunderbolt had forced a new mindset, one that acknowledged the limits of replication and emphasized innovation within constraints. And yet, as the hangar lights dimmed each evening, Tank and his team would return to the same question. How had the Americans built an engine that could endure battle after battle, while ours failed under strain? It was a question that no amount of analysis could fully answer, a haunting reminder that victory in the sky depended as much on the capacity to produce and sustain technology as on the brilliance of design. The P-47, in all its mechanical glory, had done more than expose a gap in German engineering. It had reshaped their understanding of what true technological power meant. The engine was no longer just a machine. It was a teacher, a silent instructor, whispering lessons that would echo far beyond the hangar, far beyond the war itself. The lessons of the captured P-47 did not remain confined to German hangars. Across the European skies, the impact of the Thunderbolt's engine revealed itself in stark, often brutal ways. Escorting B-17 bombers deep into the heart of the Reich, P-47 pilots discovered that their machines could endure flak, fighters, and extreme maneuvers with a resilience that was unprecedented. The R-2800 was not merely an engine, it was an enabler, turning calculated risk into survivable reality. Each successful mission reinforced the principle. Industrial robustness could trump tactical brilliance. Allied pilots spoke of it with awe. Tales of aircraft returning battered but intact, missing panels, scorched wingtips, riddled fuselages, became common. They recounted how engines continued to roar even when oil lines were punctured, fuel leaks ignored, and cylinders overtaxed. This reliability was not a quirk. It was deliberate, a reflection of meticulous American engineering combined with an understanding of the demands of total war. For the first time, the Luftwaffe faced an adversary whose machines were not only powerful, but practically indestructible in the hands of skilled crews. The Germans attempted to adapt. Engineers incorporated lessons learned from the R-2800 into new designs, tweaking cooling systems, experimenting with reinforced components, and optimizing fuel mixtures. But every adaptation highlighted a harsh truth. Without the industrial scale and resource abundance that the Americans enjoyed, their solutions remained partial, fragile, and prone to failure. The gap between ingenuity and industrial capability became painfully evident. Every P-47 lost over German territory underscored this disparity. Every captured engine, a reminder of an enemy who had turned practicality into a weapon. Operational strategy shifted as a result. Luftwaffe commanders realized that conventional tactics honed over years, were no longer sufficient. Pilots were instructed to avoid prolonged engagements with Thunderbolts whenever possible, favoring ambushes, rapid dives, and coordinated strikes. Yet even these measures were only partially effective. The P-47's ability to sustain combat, combined with its heavy armament and long range, meant that American forces increasingly dictated the terms of the engagement. Air superiority, once a contested prize, began to tilt inexorably in favor of the Allies. The consequences extended beyond the battlefield. The captured P-47 became a case study in technical literature, a touchstone for debates among German engineers, scientists, and strategists. Reports detailed the strengths of the R-2800, documenting every innovation, flaw, and difference in industrial philosophy. Each entry reinforced the sobering realization. The Americans had built a machine that balanced power, endurance, and maintainability in a way that Germany could not match under wartime constraints. Yet the story was not one of unmitigated triumph. Even with the P-47, mistakes occurred. Pilots sometimes underestimated German defenses, overextended their formations, or suffered mechanical failures unrelated to engine performance. The Thunderbolt, powerful as it was, required disciplined handling and strategic coordination. Its success was as much a testament to doctrine, training, and logistics as to engineering brilliance. Despite these challenges, the cumulative effect was undeniable. The P-47's presence forced a re-evaluation of air strategy, production priorities, and engineering philosophy. The Thunderbolt became a symbol of the Allied approach. Scale, reliability, and practical innovation could deliver results that theoretical perfection alone could not. Its influence extended beyond immediate victories, shaping post-war aviation thinking, inspiring designs for engines, airframes, and even jet propulsion systems that would dominate the next decades. In Berlin, the realization settled in with growing weight. German engineers had faced the future, captured it in metal and steel, and understood its superiority. But replication remained elusive. The captured P-47 engine, dissected and analyzed in countless ways, became both a symbol of aspiration and a monument to industrial disparity. It taught a lesson that could not be ignored. In modern warfare, the ability to produce, sustain, and adapt machines at scale could outweigh brilliance, strategy, or courage alone. By the war's end, the narrative was clear. The Americans had leveraged not only tactical skill, but the full might of industrial power. The P-47, with its mighty R-2800 engine, had proven that victory required machines that could endure the chaos of combat, and the wisdom to deploy them effectively. For German engineers, the captured Thunderbolt remained a bitter but invaluable teacher, a reminder that in the unforgiving skies of total war, practicality, resilience, and foresight could change the outcome of history itself. The captured P-47's engine had done more than power a plane. It had powered a transformation in understanding. It reshaped air tactics, industrial strategy, and the very philosophy of engineering under pressure. And for those who studied it, from Berlin to the front lines, one truth was impossible to ignore. In war, the machine that survives often decides who wins, and the engine that endures becomes the quiet hero of history. The war in Europe ended, cities lay in ruins, and the skies that once thundered with the roar of engines fell silent. Yet the lessons of those skies endured. Among them, none was more profound than the quiet lesson taught by the captured P-47 Thunderbolt and its R-2800 double-wasp engine. It was a reminder that technological brilliance alone does not secure victory. Endurance, adaptability, and the vision to sustain innovation under pressure can shape history just as decisively as courage in combat. For the German engineers who had examined the Thunderbolt, the end of the war brought reflection, and, in some cases, unexpected new beginnings. Kurt Tank and others, once confined to Luftwaffe design bureaus, were sought after by international aerospace programs. Some found their skills transplanted to post-war aviation projects in the United States, Britain, and even the Soviet Union. The captured engine they had studied in vain became a benchmark, a standard of industrial philosophy that would echo in designs for decades. In America, the P-47 became more than a wartime workhorse. It became a symbol of industrial ingenuity and practical engineering, the embodiment of a philosophy that balanced raw power, resilience, and the demands of total war. Its influence stretched beyond the battlefield, informing post-war aviation design, jet engines, and even the principles of mass production in peacetime industry. The Thunderbolt's legacy was not just in the air it had dominated, but in the thinking it inspired about how humans conceive, build, and rely on machines under pressure. Yet perhaps the most enduring lesson is philosophical. In every piston, cylinder, and crankshaft of the R-2800, there was a story of foresight and perseverance. The engine had taught that innovation is not measured solely by complexity, but by its ability to endure, to serve, and to empower those who rely on it. It had shown that progress often comes not from perfection alone, but from resilience, adaptability, and the courage to challenge existing paradigms. As historians reflect on those moments, the image of the captured P-47 persists. A machine that stopped engineers in their tracks, forcing them to confront limits they could not overcome. Standing over its massive engine, they glimpsed not just metal and mechanics, but the human capacity for ingenuity, and the sobering truth that sometimes the best machine is not the one that is most intricate, but the one that endures when everything else fails. The pilots who flew the Thunderbolt, the engineers who built it, and the adversaries who tried and failed to replicate it are linked by a singular thread: the pursuit of excellence under impossible circumstances. The R-2800 engine was more than a mechanical triumph. It was a teacher, a challenge, a reminder that in the crucible of war, every decision, every design, every moment of courage counts. And so, as the sun sets over quiet airfields and silent hangars, the lesson resonates. In the world of machines and men, the true measure of greatness is not only in speed, power, or precision, but in the resilience to endure, to perform under pressure, and to inspire those who follow. The captured Thunderbolt, in its silent metallic majesty, speaks across the decades. Innovation matters, courage matters, but endurance prevails. History remembers the pilots who soared, the engineers who designed, and the machines that made it possible. And somewhere, in the heartbeat of that mighty engine, lies a truth that transcends war, borders, and time itself. The machinery that survives, teaches, and inspires becomes the quiet hero of humanity's story.